Hello. In this video, we're going to begin a series of short videos on limit theorems of functions. These limit theorems that we will prove will be in a lot of ways similar to the limit theorems that we proved for sequences. So to begin, we're going to show that convergent functions will be bounded in some neighborhood of the limiting term. So if x is converging to c, f of x converges to some limit. If that exists, then there's some neighborhood around c for which the function is bounded. It's no larger than in magnitude than some positive real number. So formally, the definition of being bounded, so suppose that a is some subset of the real numbers, f is a function that maps a to r, and c is a cluster point of a. We say that f is bounded on a neighborhood of c if there exists a delta neighborhood around c and a constant m, positive number, so that in magnitude the function is no more than m for any x that intersects a in that neighborhood. Okay, so and this would make sense. You would imagine that as x goes to c, if f converges to some number L, right, then there has to be some neighborhood around c for which the function is not going to deviate infinitely far away from the limit, right? So it would make sense that if this if the function does converge, then there has to be one of these neighborhoods, right? And that's the theorem that we're going to prove in this video. I think the numbering is 4.2.2. There. Let me double check that. I think it is. Okay. So this states that if A is some subset of real numbers, if F maps A to R, and what is the language they use? And I'll just use this, and limit as x goes to c of f exists. So this is worded slightly different than in your textbook. So we have some set of real numbers, f maps a to r, and we're supposing that the limit exists. Then f is bounded on some delta neighborhood of c. Okay, so then f is bounded on some neighborhood of c. Okay, this is precisely what I was kind of hinting at, or not hinting at, but saying a moment ago. Like it would make sense that if the function does converge to a limit as x approaches c, then somewhere around c, the function is not going to be arbitrarily far away from the limit. That's what this is saying. Now, this is going to be a very similar proof to what we did with sequences. In particular, we're going to use this notion of convergence, choose an epsilon to be some finite number, for example, epsilon equals to 1, and then show that the function is bounded by using the reverse triangle inequality. So it's a very simple idea, but you'll see it happen over and over again in real analysis. So let's look at the proof. So I'm going to say, suppose the limit exists and it equals to some number L. So suppose limit as x approaches c of f is equal to L, which means we can use the definition of convergence, which is an epsilon delta definition. So now I'm going to choose my epsilon. So suppose that equals to L, and choose epsilon equal to 1. Okay. So then by definition, there's a delta, right? So we'll just say it out loud, or write it out, I mean. So then by definition, there is some positive delta. There exists delta greater than 0. So that's 0 less than x minus c less than delta. So the distance from x to c is at most delta, and x doesn't equal c. So when that's the case, this implies that the distance from the function to the limit is less than epsilon, but epsilon is equal to 1. Okay. So that is that if we, maybe I should write it out. So that is, or maybe I'll use like thus or something like. So thus, if we apply the triangle inequality, I suppose, we have that the absolute value of f of x minus the absolute value of L is at most the absolute value of f of x minus L, which is at most 1. That looks ugly. Which this holds if and only if the absolute value of f of x is at most 1 plus absolute value of L. In that, this inequality here holds whenever this holds, right? Or in other words, i.e., if x is in that delta neighborhood of C, set difference C. And the strictly greater than 0 means that x can't equal to C, but otherwise this is in that neighborhood. So this holds whenever x is in the delta neighborhood of C, set difference C. Okay. Thus, or hence, oh no, I'll say therefore, f of x is bounded on a delta neighborhood of C since the magnitude of f of x is at most 1 plus the absolute value of L. If x is not contained in A, and the absolute value of f of x is at most the max or the suit absolute value of C, comma 1 plus the absolute value of L, if x is in it. Or no, what am I doing? Not x, C. if C is in A. Because if C is in A, and we want the function to be bounded on all values in the neighborhood of C intersect A, if C is in A, then we have to also consider f of C. So if C isn't in A, then f of x is bounded above by 1 plus the limit. If C is in A, then f of x is bounded above by these values here for any x in the neighborhood of C, in the delta neighborhood of C. And that's it. We've shown that it's bounded. First, because in this case here, this would be our M. In this case here, that would be our M satisfying the definition, and we're done. Okay. All right, so that will conclude this first video on limit theorems. And in the next video, we're going to prove the basic limit theorems on sums of functions, differences of functions, quotients of functions, products of functions. These basic facts that you see in Calculus 1, we're going to prove those formally, but rather quickly in the next video. Thank you for watching.